Good day, students. Welcome to mathgotserved.com. And this clip we're going to be going over question number 23 of our collection of math induction problems. We're going to be proving that 4n squared plus 12n is divisible by 8 using the method of mathematical induction. Don't forget, we have tons of examples that you can access in the description below. Just scroll down and then you can take a look at the link. That will take you to a page that has all the examples that we've done so far and the corresponding videos explaining how the proofs are done. Don't forget to support our channel by giving us a thumbs up, a like, and a share. Alright, so the proof we're doing today, again, is as follows. We're going to prove that 4n squared plus 12n is divisible by 8. We want to prove that that statement is true for all positive integers n. Alrighty, the plan of attack is on the yellow box to the right. That's what we're going to be following. Let's go over that real quick. First of all, we're going to state what the base case is. We're going to show that the base case is true, basically showing that the statement holds for n equals 1, since that's the first positive integer. And then we're going to state what the inductive hypothesis is, which is just assuming that the statement is true for any arbitrary integer k. And then using that, assuming that that is true, we're going to use the inductive step to show that if the inductive hypothesis is true, it follows that then it's true for the next case, namely n equals k plus 1. Alright, so using the combination of these three, we can show that the statement is true for all positive integers. And then that will be captured in our conclusion. Alright, so let's go ahead and get started. So we have this problem presented in verbal format. Of course, we want to write a mathematical proof. So we have to convert this statement into a symbolic form. Okay, write it as an equation that we can use to carry out our proofs. So let's do the first step, which is to write the statement in as an equation. Okay, write a statement as an equation. So how do you write a divisibility statement by a certain integer as a statement? So this is how we're going to write it. So the statement 4n squared plus 12n is divisible. I'm just going to use the word the abbreviation div for time reasons. Is divisible by 8. To write this as in symbolic format, we're going to say S sub n is 4n squared plus 12n is equal to 8k. Alright, for some integer k, or some positive integer k. Alright, so if you can write a number in the form 8 times a positive integer, then that automatically shows that that number is divisible by 8. Okay, so this is just a symbolic format of writing what we're going to prove. Okay, writing it like this is easy for us to go through our base case, inductive hypothesis, and inductive step. Let's start with the first part of our proof, which is the base case. Okay, so the base case is not always n equals 1. You have to pay close attention to the statement. Okay, sometimes it could be 3 or 4 or 2, so it's not always 1. In this particular case, is 1. So in this case, the base case is positive integers. So we want to show that the statement is true when n is equal to the base, the first positive integer, which is 1. So s sub 1, we want to show that s sub 1 is true. Basically, if we substitute 1 for n, we have a statement, we have an expression that can be written as a multiple, a number that can be written as a multiple of 8. That's the whole idea. Okay. Alright, so s sub 1, we have a situation where all the n's are replaced with 1. So we have 4 times 1 squared plus 12 times 1. Okay, so this is what you get when you substitute 1 into the statement. Now let's use the order of operations to simplify this. 4 times 1 squared is just 4 plus 12. That's 16. Now, can this number 16 be written as a multiple, an integer multiple of 8? Absolutely. 16 can be written as 8 times 2. Okay, so since 16 can be written as an integer multiple of 8, what does that tell us? It shows that this clearly shows S sub 1 is true, right? Because we have a situation where S sub 1 is divisible by 8. We just showed it because S sub 1 is 16, which is divisible by 8. Bam. Alright, so there goes our base case. We have our foundation together now. Now we're going to set up our inductive hypothesis. We're just going to make an assumption, okay? So we pick any random integer in the set of positive integers and we assume that that's true. Then that will be a basis for us to go into our next inductive step, okay? So for the inductive hypothesis, let's make the following induction. Inductive hypothesis. In this particular case, we just assume that S sub k is true. Assume that S sub k is true. Basically, when you substitute some integer, you pick some integer k, some random integer k, and you put it into the statement, you end up with a true statement. Okay? Alright, so let's do it. So for the inductive hypothesis, this is what we're going to assume. We're going to assume that the statement S sub k, which is 4k squared plus 12k, is divisible by 8. How do we show that it's divisible by 8? We assume that if S sub k is true, if 4k squared plus 12k is divisible by 8, then using this system that we have established here, this number can be written, or this expression can be written as a multiple of 8 is equal to 8m. So this statement is true for some integers for some integers k and m, okay? Alright, so assuming that this statement is true. So for some positive integers k and m, this statement here is true. So this is our inductive hypothesis. Now, what is the beauty of inductive hypothesis? Well, when we're carrying out the next step, which is inductive step, we're always going to use our inductive hypothesis to complete that step. Alright, so let's assume that this statement 4k squared plus 12k equals 8m is true for some integers k and m. Okay, now the inductive step. Taking one integer step from the inductive hypothesis. So for the inductive step, our goal here is to show that if the inductive hypothesis is true, it follows that the next step, namely k plus 1, is also true. So let's just write down what we're going to do here. So we want to show that S of k is true. It's just like a domino, right? Automatically follows that the next step, S sub k plus 1, is true. So that basically shows that the statement will be true for all positive integers. That's the beauty of mathematical induction. Okay, so now what we're going to do right now is we're going to start with our S sub k plus 1 statement, simplify it as much as we can, and then we're going to use some substitutions with our inductive hypothesis to show that S of k plus 1, the inductive step, is also true. Namely, it's divisible by 8. That's the ultimate goal. Okay? Alright, so what is S sub k plus 1? Let's go ahead and write that down. S sub k plus 1 is the statement you get when you substitute k plus 1 into our original statement. So S sub k plus 1 is going to be 4 times, instead of n squared, we're going to use k plus 1 squared plus 12. Instead of n, we have 12 times k plus 1. Okay. All right. Now we're going to simplify this completely. So let's go ahead and do that. All right. So we're going to go ahead and expand this. We have quantity 4k, k plus 1 squared. So just multiply k plus 1 by itself twice, and then distribute 12 across k plus 1. So that gives us 12k plus 12. Okay, and if we expand k plus 1 square, or k plus 1 times k plus 1, we have 4 times k squared plus 2k plus 1 plus 12k plus 12. Using the formula a plus b squared equals a squared plus 2ab plus b squared. That's a fast way to expand this. If not, you can just FOIL it out, combine the middle terms, and then that's where you get the 2k. Okay. All right. So you distribute the 4 across the quadratic trinomial. So we have 4k squared plus 8k plus 4 plus 12k plus 12. All right. So now what we're going to do in the way we're going to rewrite this, we have to have a target in mind. We're not just going to simplify it all the way. Okay. So the first task is as follows. Is there a way where we can extract this expression 4k squared plus 12k from this expression we have right here? Is there any way we can isolate a combination of these two terms? Certainly. We have 4k squared here, and we have 12k right there, so we just put them next to each other, and then we'll bother with the rest after that. See what we can do with those. Okay. All right. So if we rewrite, we're gonna have 4k squared, and then commute 12k here over here, plus 12k, and then we're left with what? We're left with 8k plus 4 plus 12. 4 plus 12 is 16. Okay. Bam. All right. Now, what can we do? Well, we know that 4k squared plus 12k is divisible by 8. How do we know that? Well, by our assumption in the inductive hypothesis part 2, we said 4k squared plus 12k, we assume that it's divisible by 8. Basically, that is equal to 8m for some integers k and m. So what does that enable us to do? We can now carry out a substitution. Based on our inductive hypothesis, we can replace 4k squared plus 12k with 8m. All right. And then if you notice these two terms here, you can factor out 8 from them. So factor out 8, and then you have 8 times quantity k plus 2. All right. We know that integers are closed under addition and subtraction. Basically, whenever you add and subtract integers, you end up with integers, right? So if you're adding two integers, k plus 2, it's also going to be an integer. All right. So let's replace that with some other integer. So let's just say let k plus 2 equals L, okay, for some integer L. For some integer L. All right. Now we can make a substitution. This becomes 8m plus 8l. Let's write that again so it looks nice. So this becomes 8m plus 8l. Okay. Now what can we do here? Oh, we notice that we can factor out 8 from these two terms. So we factor out 8 again, factor out 8, and then we have 8 times the quantity m plus l. Now we stated earlier that integers are closed under addition and subtraction. Okay, they also closed under multiplication, but when it comes to division, not so much. So when we're adding two integers, we know that we're also going to get an integer. All right, if you add two positive integers, you always end up with a positive integer. Okay, so we can make another substitution here. How about we replace m and l with some integer? Let's say j. Okay, so let m plus l, integers m plus l equals j for some positive integer j. Okay, all the letters we're using in this problem are all positive integers. All right, we are moving forward. We're just adding, moving to the right. There's no movement backwards. So we start with our base case, and then we're picking positive integers after that. Okay, now we can make a substitution. Okay, and we'll make a substitution. We can write this as 8j. So let's rewrite the whole statement again. The statement s sub k plus 1, our inductive statement step, s sub k plus 1 is equal to 8j. Bam. You see that? So what does this tell us? S sub k plus 1 is equal to 8j for some positive integer j, tells us that s sub k plus 1 is also true. Namely, it is divisible by 8. Remember, s sub n statement means that whatever is represented is divisible by 8. So s sub k plus 1 can be written as an integer multiple of 8. It automatically shows that s sub k plus 1 is a statement that inductive step is divisible by 8. Okay, so s sub k plus 1 is true. Let's write out exactly what this statement means. Let's write it in verbal form. S sub k plus 1 is true since this statement means that s sub k plus 1 is divisible by 8. That's exactly what this equation is telling us. Okay, so now let's go ahead and write down what our conclusion is, what all these mean. Let's write down our conclusion, which is as follows. All right, so in conclusion, since s of 1 is true, okay, since s of 1 is true and s sub k is true, implies that s sub k plus 1 is also true. Basically, the inductive hypothesis implies that the inductive step is true. S sub k plus 1 is also true for some positive integer k. So my computer's acting up. For some positive integer k, then what? Then the statement for n square, then the statement 4n square plus 12n is divisible by 8 is true for all positive integers. For all positive integers. All right, so that's basically the proof of the statement using the method of induction. So let us know your thoughts in the comment section below. How difficult will you rate this proof on a scale from 1 to 10? What are some parts that you found easy to follow? What are some parts that were difficult? Let us know in the comment section below so that we can use your feedback to influence the development of our next tutorials on induction. Thanks so much for taking the time to watch this presentation. I really appreciate it. As indicated earlier, we have a wide collection of induction tutorials in the description below. Do check it out. And also visit our website at mathgotserved.com for tons of support resources in different levels of math. Thanks again for watching and have a wonderful day. Goodbye.